Hey guys, this commences the first semester exam review guide, and I'm going to do one section at a time so the videos aren't really long. So this is the best way you can study for my exam to understand these questions. I'm going to base my exam on these kind of questions. Okay? So let's get started. Okay, you can find this review sheet in the last module on Canvas. Okay, so first section I want to talk, these are in chronological order. So, um, we're going to start with vector versus scalars and how to add vectors. Okay, so let's start with a displacement problem. Okay, again, displacement, that's my starting point, and I walk like this, and I end right there. My displacement is defined as a straight line distance from the start to the finish, that represented by that arrow right there. Okay, it's a vector. A vector has both direction and size. So basically, displacement is a good example of a vector. So I like to use arrows on these kind of questions to represent the different displacements. So if you walk 13 miles north, okay, I'm going to write an arrow going, make that 13 miles north. And then I drive 2 miles south. Okay, make the arrow much smaller because 2 is much less. And south means -2. Downwards is negative, upwards is positive, or north is positive, south is negative. Okay, so the south for displacement, distance from the start to the finish, in the direction from the start to the finish, is represented by that arrow, from the start to the head of the last arrow. So we can just do the math. 13 plus a -2 is equal to 11 miles. Okay, and I have to mention the direction. Okay, if they said what's the magnitude of the net displacement, I'm done right there. But if I said what is the net displacement, I have to add the direction. Where's the direction? From the start to the finish, it would be north. So there's my answer there. Okay, let's go to number 2. Plane is flying 125 due east, so east, I'm going to make to the right, make that positive. All of a sudden, a wind begins to blow, a tailwind. So, heads to tail. It gets, what was that, 125 meters per second, and then heads to tail, same direction, so much smaller, 12. What is the plane's net velocity? Velocity is a vector. Velocity is speed in some direction. So my net velocity would equal 125 plus 12, which is equal to 137. 137 meters per second. Then I had to mention the direction because they're asking for the velocity, not just the magnitude of velocity. So that would be from the start to the finish would be, as you can easily see and probably do in your head, it would be east. So there's my answer there. Okay, let's go back to number 1. What I found in number 1 was d net, and we put a little harpoon on it to represent net displacement, to represent vectors. Okay, I'm not really going to use those symbols on my test, but that's what I did before. Okay, let's look at number 3. What is the difference between a scalar quantity and a vector quantity? Okay, you should be able to do this readily. Scalar just has magnitude, which is size. So they're both measurements. But scalar just has magnitude only. Magnitude is number in a unit. Size. It's another word for magnitude. So like 12 meters per second. That is a vector. That would be speed. But I'm sorry, made that wrong. 12 meters per second is a scalar. That would be speed because there's no direction. If I said 12 meters per second east, talking about a vector. So a vector has magnitude, of course, and direction. You got to specify the direction. Okay, example would be 12 meters per second east, velocity. So if we were to list some vectors and compare to scalars, scalar would be time, speed. I use the S for speed like positive physics did. Distance, mass, and then temperature also, but we're not going to get. Okay, vectors, examples of vectors would be time, not time, but velocity, displacement, force, acceleration. Okay, those are the ones we talked about so far. Okay, you should know these. Any kind of force. Weight would be a vector. Tension would be a vector. Friction would be a vector. Net force would be a vector. Drag would be a vector. Thrust would be a vector. Whatever. Okay, so those are examples of vectors. Okay, here's another vector addition problem, but it's a little fancier. Let's write in my book. I ride 3 miles south and 4 miles east. Why is this a little bit more difficult? Okay, south, and then I go east, 4 miles. You can't just add and subtract when you have angles between the vectors. So this would be the net displacement right here from the start to the finish. And you can do, it could be any angle between the two vectors, but we've only taught you how to do right angles between the vectors. So this d net, you should see net displacement would be figured out using Pythagorean theorem because it's always going to be a right angled triangle for us. So 9 plus 16 is 25. Square root of 25 is equal to 5 meters. No, miles we're talking about. So that's the net displacement. So if the vectors aren't aligned, collinear, you're going to have to, the angle will only be perpendicular, 90 degrees. You have to use Pythagorean theorem, heads or tail method, and then start to finish, draw the hypotenuse, find the hypotenuse using Pythagorean theorem. Well, that was the net displacement. Now to find the net distance, that's basic. Net distance, you do what? Remember the difference between the symbols. There's a harpoon on the D net. There's no harpoon on the D net if it's distance. There's a harpoon if it's displacement. So you just add them. 3 plus 4. I don't care what directions they go. It's like an odometer reading. So you can see that the distance covered is not the displacement. 7 is not the same as 5. Okay. So using the same problem, remember we did this on the test with that, all those blocks, city blocks. I don't know if you remember, but anyway, the south trip takes 10 minutes and the east trip takes 20 minutes. What's my average speed? Well, average speed, instead of some kinematics here, is equal to total distance over the time. So the total distance is 7 from what we just did, miles. Total time, let's see, 10 minutes for the south, 20 minutes for the east. So 10 plus 20 is 30. I just add the total to find the total time. So I'm not going to work this out. Take my calculator and work it out. So this is just 730. It's meters per second, miles per minute. Watch out. I almost put meters per second. Miles per minute. Because that's what I have. Minutes and miles. That's what I've been given. What's my average velocity? It's the displacement over the time. The net displacement, which would be 5 over 30. 1, 2, 3, 4, 5, 6. 1/6 miles per minute. You can see that these are nowhere near the same numbers. Okay, I would calculate it out. You can do that part. Okay, now we go to motion graphs. Let's look at distance versus time graphs in this section. First thing about D versus T graphs, it's really displacement versus time, or position versus time. But I just call them D versus T. So we're supposed to find the is the constant velocity or okay, wait. Most important thing on a D versus T graph is the slope, rise over run, is equal to what? The velocity. That is the most important thing when I ask questions about these graphs. Okay, so the rise over run is equal to velocity. Okay, so let's analyze these different kind of graphs. Okay, so is it constant velocity or constant acceleration? Okay, first of all, constant acceleration, let's write that over here. Constant acceleration means one of two things. Either you're stopped, either you're at rest, or you're moving with constant speed. Sorry about that. I'm messing this up. Zero acceleration. Here, let's not even worry about it yet. I'm jumping ahead too quickly here. Okay, so the, the velocity is the slope on a d versus t graph. So as long as the line is straight, there is velocity, constant velocity. I mean, so it's a, for example, right here, right here, right here, the slope is the same in any of those points. So the velocity is the same at any of those points. And if the line, the graph line on a d versus t graph is straight, then the slope is constant. That means slope is velocity. That means the velocity is constant. So I'm going to say constant velocity on that one. So I'm just going to go down the line here. And wherever the line's straight, I'm going to say constant velocity. If the line's curved, it has acceleration. Because right here, use the magic pencil. The speed is increasing there. Right here, use the magic pencil. Ride your pencil down the graph like a sled. The slope increases. So the speed is increasing, so it can't be constant speed. It has to be accelerating. That's why I put an A there. Because the next one is the positive or negative velocity. This is really easy. If it's going uphill, it's positive velocity. If it's going downhill, that's negative slope. That means negative velocity. What does that mean? Positive velocity means going in the positive direction, moving in the positive direction, either up or to the right. Negative velocity, downhill slopes on a d versus t graph, means going the negative direction, moving in a negative direction, which would mean moving to the left or down or to the west. Okay, so we can see that which ones have negative slope. Well, the first one is going downhill, so that's negative velocity. That doesn't mean the speed's decreasing. That just means the direction the object's moving. Number 3, I guess I'm going right to left. Number 3, going uphill, positive velocity. Number 2, going uphill, positive velocity. The next one, number 4, negative velocity is going downhill. It means it's going to the left or down. Okay, number 6, going uphill. Even though it's not going uphill steadily, at constant speed is. So I'm going to say uphill, positive velocity. Number 5, downhill. Okay. Next one's kind of relative to the other pictures. Is it moving fast or slow? Is it speeding up or slowing down? Or staying constant? We already talked about constant. Okay, that's the steepness of the slope, how big the slope is. Similar in the first one, it looks pretty steep to me, but it's going constant speed, like I said before. So it's going kind of fast in the negative direction with a constant speed. Number 3, looks like it's going fast, but in the positive direction because it's steep. Look at number 2, kind of flat. I mean, not so steep. So it's going slow compared to the other guys, assuming the scale's the same on all these graphs. I should have said that. Number 4 looks like it's slow too. It's not so steep. So number 6, it looks like it starts out slow with a not so steep magic pencil. Then it gets steeper and steeper. So it speeds up. The speed is increasing. And number two, and the final one, the magic pencil is getting steeper and steeper. So this is decreasing speed. Okay, you guys remember? Oh, I'm not going to go through that yet. Let's do the next one. Object moving forward. What am I supposed to do? Sketch a graph. Okay. Object moving forward. That's to the right. I'm assuming forward is to the right with a steady constant speed. Okay, so doesn't matter. Something like that. Moving forward means positive velocity, I'm assuming, and a steady constant speed. An object standing still. That means the speed is zero. Means the slope is zero. So that'd be a horizontal line anywhere. Doesn't matter how high or how low it is. Object changes directions. Wow. I have to have, I'm making these points zero. So if an object changes direction, it has to go from positive to negative velocity or from negative velocity to positive velocity. So either like this, or you could do just as easily, you could have negative velocity going to positive velocity. Okay, so in the red one, I have positive velocity going to negative velocity. Then that's change of directions. Plus forward, minus going downhill, in reverse, going back. An object moving backwards with a steady constant velocity. Okay, that would just be negative velocity, steady, straight line. Object speeds up, then slows down. Okay, so we got the magic pencil going up like this. Curve, it has to be a curve, it's speeding up. Then it slows down. Okay, so the magic pencil flattens out. So it looks like a S. Let me do that again. So object speeds up, then it slows down. So at that point, it starts slowing down, but I didn't change direction. Now I could just as easily done it like this. Object speeds up, then it slows down. I could have just easily drawn it like that because magic pencil's getting steeper and then it gets flatter. An object which accelerates, well, that could be anything. It could be this, any curved line, any curved line. This, second half of a smile, second half of a frown, first half of a smile, second half of a, no, first half of a frown. So any of those lines represent acceleration because they're not straight. Okay, this graph represents a short car trip. Find the velocity of the car for each part of the trip. Okay, we're still on V versus T graphs between points A and B. Okay, so this is just finding slopes, being sure you can find slopes. So between A and B, I draw a triangle, biggest one I can. Okay, the rise is 6 minus 0. Okay, so velocity is the rise over the run. So it's positive 6 over what's the run? That's only 2. Watch out, they change. Yeah, every block is 2 up and down. Okay, so that's 3 meters per second looking at the units that they have. Okay, between points B and C. A flat line, a D versus T graph means zero velocity. You can see it, there's no rise because it's flat, it's horizontal. Okay, between C and D. Okay, I don't know. I don't know exactly. I'm going to estimate that it's 9 there and it's 5 there. So the run is 9 minus 5 is 4. The rise looks like it's 10 minus 6 is 4. So 4 over 4 is 1 meters per second. It's going uphill, so it's positive. Between D and E, that's 0 again, flat. Between E and F, oops. The rise looks like it's 10 minus negative 2. Watch out. 10 minus the negative 2. Actually, it's the final minus the original, so it's negative 2 minus 10. But I just do it this way, and then I put a negative on the total answer because I know it's going down. And the run looks like it's 1.5 blocks. So from 11 to 14 is 3. So that'd be 12 thirds, which is 4 meters per second. But it's negative 4 because it's going downhill. It's negative 4 because it's going downhill. Okay? Now that looks like it's the same slope as your answer for 8 between C and D. But it isn't. So let's double check. 4 divided by... Okay? So 10 minus negative 12. Okay, so 10 minus negative 2 is 12. Then that's over 3. So supposedly, what? Oh, wait. I'm wrong. So that's right. Everything I've done is right so far. Okay, what's the average speed for this entire trip? Okay, a little tricky. Speed is what? Distance over time. Okay, the total distance. You gotta be careful. Okay, let's do this. I'll make this a little smaller. Okay, from A to B, I went 6. I'm gonna keep a running chart up here. From B to C, I didn't go anywhere, right? From C to D, I went another 2. Okay, or I can say 10 for the total A to B. So I'll just say I traveled another 2 blocks, which would be 4. Okay, it says right there. Okay, and then D to E, I didn't go anywhere. Then E to F, I went 12 from 10 to negative 2, right? I'm not going to put a negative on it because I'm talking about distance. So I went back down from here all the way down to there. From E to F. Then F to G, I did another 12. Okay? Going from there to there, I did another 12. Okay, so 24 plus 4, 28 plus 1, 2, 3, 4, 5, 6, 34. So I did the total distance you travel was 34 meters. I add all those different distances up. 24 plus 4, 28, 34. Okay, so my speed is 34 over the total time, which looks like 16. So you can calculate that out, meters per second. What's the total velocity? I mean, what's the average velocity of the trip? That's displacement over time. Displacement is from the start to the finish. Okay, so let's do a different color. Okay, here's the starting point. Happens to be 0 right there. And where's the finish point? Way up here. So from the start to the finish, is positive 10. From start to the finish, here to there is positive 10. So that'd be 10. Be 10 over the same amount of time. 16, 5/8 meters per second, and it'd be positive because he ends up above the starting point. Okay, so I'd be able to do that with a d versus t graph. Okay, velocity versus time graphs. Okay, this is where I'll stop for this first video after I finish this. Most important thing about velocity versus time graph is the slope is equal to the acceleration. Okay, slope is equal to the acceleration. That's the most important thing on a v versus t graph. Okay, so object motion is what? Put all there true. Is it moving in the positive direction? Okay, on v versus t graph, if you're in this region up there above the 0, your positive velocity. Not if you're going uphill or not. Okay, so if you're in that region up here above the 0, because you're going positive velocity. If you're down below 0, like over here, you have negative velocity. That means going in the negative direction. So you're moving in the positive direction? Yeah, I never went to the negative zone, the southern hemisphere, where it's all negative. So, yes, it's true. I'm only moving in the positive direction. Am I moving with constant velocity? No. Right here, look, the velocity is doing what? The y-axis is velocity. The velocity is decreasing. So, no. Moving with a negative velocity. No, we said it's only moving with positive velocity. It would have to go into that region below the x-axis to go into negative velocity. Is it slowing down? Yes, it is slowing down because with time passing, you see my lines I drew, the parallel, the horizontal lines to the y-axis, is getting closer and closer to 0. Is it changing directions? No. Is it speeding? To change direction, it has to move across the x-axis and go into the other zone. Is it speeding up? No. It's only slowing down. Is it moving with a positive acceleration? Okay, acceleration is the slope. It's going downhill, so it's negative acceleration. So no, it's not moving with positive acceleration. Is it moving with a constant acceleration? Yes, it is. The line is straight. The slope is acceleration. The slope at any point on a straight line is identical to the other points on that line. So yes, moving with a constant negative acceleration. So those three things are right. Okay. Starting to rain out here. Let me move my position. Okay, here we have another velocity versus time graph. Determine the acceleration of the rocket during the listed time intervals. Okay, you just find the slopes. Because again, on a v versus t graph, slope is equal to the acceleration. So for 0 to 1 seconds, slope is 40 divided by 1. The rise over run, 40 over 1, equals 40 meters per second squared. Recognize that unit, meters per second over second, meter per second squared. For 1 to 4 seconds, wiping the raindrops off. Okay, so from 1 to 4 seconds, from 1 to 4 seconds, 4 minus 1 is 3 for the run. 100 minus 40 is 60 for the rise. Rise over run, 60 over 3 is 20 meters per second squared. Okay, positive because it's going uphill. 4 to 12 seconds. Okay, I see that's a straight line, so I don't have to do the whole thing. I can pick any box here. Looks like I can pick that one. Or I could pick this one. Or I could pick the whole entire shooting match. Let's pick the easy. If it hits corners of a grid box, you're fine. So, looks like it's 60 minus 40 is 20 for the rise. And the run looks like it's 6 to 7, 1. But it's negative 20 meters per second squared. Negative because it's going downhill. Okay, let's just double check. What if we did the entire triangle? 100 minus a negative 60 is 160 divided by that whole run. 12 minus 4 is 8. 160 divided by 8. 160 divided by 8 is 20. And again, it's negative. So it doesn't matter what triangle you pick, just so that it hits the corners of a grid box. Okay, again, don't forget that uphill lines are positive slopes and downhill lines are negative slopes. Describe motion by the following. Okay, is the speed increasing or decreasing? Is it going faster or slower? Blah, blah, blah. Okay, so this is a V versus T graph. Okay, so yeah, it looks like let me just erase this part right here. Okay, so this one is B right here. My format got mixed up a little bit when I put it to notability. It's number 4. Okay, so right here we got at A. This is going to be kind of hard to do because I don't have very much space. Sorry. Okay, at A, we can say that it's positive velocity. Oops. At A is positive velocity, right? Because it's in this region right here, above the x-axis, in that region. It's staying constant because it's not changing, because it's a flat line, horizontal line. So it's zero acceleration right there. If you're going constant speed, you have zero acceleration. Very important point. You could either be at rest, or going constant speed, and then you'll have zero acceleration. So that's at A. At B, we have positive velocity. That means going towards the right, but the velocity is obviously decreasing. We got constant acceleration right there because it's a straight line. We'll always have constant acceleration throughout B. Okay, so what's happening there is you have, what am I trying to get at? You have negative acceleration. Negative acceleration because it's downhill slope. Now, remember what we said? This is important for the test. If V and A have opposite signs, the speed will always be decreasing. So that's kind of a check. Then again at C, it's the same thing as at A. We got positive velocity, but it's flat, so it's constant. And we got zero acceleration because the speed's staying constant. Okay? You can see that it's slower. It's moving slower at C here. The relative speed. What do I mean by that? Okay, so at C it's going slower than it's going at A. And it's slowing down in section B. Okay, you should know that. I mean, that should be obvious. Okay, let's look at letter B. Section A. Looking at the big picture up there. We got positive velocity because it's still above the x-axis. We got negative acceleration, okay, because the slope is negative. Slope of a v versus t graph is acceleration. And we got the speed decreasing because it's getting closer to the line is getting closer to zero, but also because if V and A have opposite signs, then the speed is decreasing. So decreasing speed. Okay. At B, actually, we have zero velocity, right? Because it's right on the x-axis. It's right on the x-axis. See, zero velocity. So if you're at rest, you have to have acceleration is zero, and the speed is not increasing or decreasing because it's at zero. That's pretty easy. This one, we have speed increasing because it's getting away from zero to higher negative numbers. Well, so we have negative velocity because it's in that region below the x-axis. Look, negative values are right there. And we got negative acceleration because it's a downhill slope. Two negatives help each other, so the speed is increasing because it's getting further away from zero, like from -1, 0, -1, -2, -3, -4. Those are getting bigger in magnitude. Okay, that's kind of confusing to some people. But if that's confusing, just look at the signs. If the signs are the same on V and A, the speed has to be increasing. Okay, right here on the last one. Okay, same thing as it was before. I mean, we can just, let's just do it again, just for practice. Right here, we have positive velocity, it's going to the right. The speed staying constant, so constant s, constant at speed, and so that'd be zero acceleration. There's no slope. There's no slope there. Going to B, well, B is just like it was before. It's positive velocity in part A. It's just the same. But the speed is getting closer to zero. So it's decreasing speed. It's getting closer to the baseline, to the X line, the X axis, sorry. And it's negative acceleration. Again, plus V plus negative A. I'm sorry, when the signs are opposites, the speed has to be decreasing. Okay, right there, it's actually stopped for a moment because it hit the x-axis. Then in C, we got what? We got negative velocity because it's below the x-axis on V versus T. We got negative acceleration because the slope is downhill. Slope on a V versus T is acceleration. And we have, because V and A are the same signs, we got speed increasing. Okay, it's getting further away from the zero value to higher negative numbers. I mean, bigger magnitude negative numbers. Okay, determine the acceleration of the object in the V versus T graph on the right. Well, that's easy. Oh, why did I do this? Because so you don't just go 25 divided by 5. Okay, a lot of people go, oh, it's just a slope. Acceleration is a slope. I got plenty of space, so let's get rid of this. Okay, so it's a slope, but be careful. The rise is 25 minus 5. So it's 20. Don't say it's 25. That's a big mistake people make on my test. This exam, because I gave you one like that. 20 is the rise. 25 minus 5. And then the run is 5. So acceleration slope on V versus T graph. So it's 20 divided by 5 equal, hey, I don't keep on showing you the harpoon anymore. But acceleration is a vector because it's plus or minus. Okay, 20 divided by 5 is 4 meters per second squared. It is not 25 over 5 meters per second squared. That would be like that, and it isn't like that. Okay, so that's where I'm going to stop this first video. We've reviewed vectors and scalars. We've done vector addition, and we've analyzed motion graphs, both D versus T graphs, position versus time graphs, and velocity versus time graphs. Okay, so I'll see you guys in the next video.